Welcome to section 8.2 of Pre-Calculus 30. Today we're going to be applying the same old transformations, a, b, h, and k, this time to logarithmic functions. So I've included a little warm-up here, sketching a couple graphs. We probably have enough practice with that by now. If you want, just plug them into Desmos or do whatever you need to do if you need to take a look at them and see how they go. But here, I'll answer a couple quick questions. Both graphs drawn above for log base 2x and log base 3x have the following in common. So both the log graphs. Now, the x-intercept would be obviously where they both cross the x-axis. So if you figure out where y equals 0, so this is basically 3 to the y equals x. Where y equals 0, the x value is going to be 1. That's right here. Both of those graphs will cross the x-axis at 1 and 0. The asymptote for these logarithmic functions. Now the asymptote for your exponential curves is the x-axis. So we might as well just take a quick look. Okay. Oh yeah, I had them ready to go. Alright. So log base 2x and log base 3x, they both cross at 1 and 0. And of course the asymptote is the vertical axis here. We never cross the y-axis, so there will never be a y-intercept. So the asymptote is the x equals 0 line. The domain, only x values from here to the right, and it will never be 0, so x such that x is always greater than 0, but otherwise an element of the reals. Okay, and the range, this will go down to negative infinity, this will continue on to positive infinity. So the range is y such that y is an element of the reals. There are absolutely no restrictions on the range. Okay, use your TI-82, which we don't have, so use Desmos. Graph these on the Cartesian plane. Log x, 3 log x, 3 log blah 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 blah. We got a whole bunch of these, and I have prepared them already so that I don't have to waste a lot of time. So there's log x, 3 log x. Okay, so notice they have the exact same x-intercept. There's 3 log half x. Now, here is where we actually get into a shift in the x-intercept. And notice that it's 2, not 1/2, which is kind of weird. So 3 log 1/2 times x plus 4. Now, within this, we have applied a horizontal shift and a stretch here. So the stretch by the factor of half would put us right here, and then the horizontal shift 4 left would move us 1, 2, 3, 4 left. So if you apply them in that order, it makes sense that we end up at -2 and 0. So we started our regular 1, and the stretch of a half ends up multiplying your x value by 2. So the mapping is fairly easy, just 1 over b. And 3 log 1/2 x plus 4 plus 1. So again, we take and we apply everything that we applied up here. Now we apply the horizontal shift left 4, and then accompanied by a vertical shift up 1. And of course we're not going to be able to tap on this value because it's not an intercept. But we can tap on this one, and you see that this one would be 0.903, and this one is shifted up 1 because of this, the vertical shift up. So again, the A, B, H, and K, these are nothing new. They have the same effect on the logarithmic graphs as they've had on all the other graphs we've looked at so far this year pretty much. So here we go. Summary. The graph of y equals log base cx is transformed into y equals a log base c b times x minus h plus k with the following parameter effects. And you know most of this already. A is a stretch. Now, what kind of stretch does A apply? Let's take a look. So we start off with our green one was our original function, then purple was our stretched by a factor of A. So green was like this, purple was stretched. Now, we haven't changed. So it's a stretch of the y value. So it's a multiplicative factor of the y value here. So if we took this, for example, and we made the exact same thing, but with, if it's going to cooperate with me, then you would notice, okay, let's get rid of all the background stuff here. Without the stretch value here, now we have a new intercept, but, oh yeah, that's because this, sorry, oops. Wheels are falling off. Okay, there we go. Now, since the value of the intercept doesn't change, this must be a stretch of the y value because we multiply the 0 by a multiplicative factor of 3. So you notice that nothing changes in terms of that value. We just get a much kind of steeper looking line. Okay? So this is a vertical stretch. So it affects the y value. Vertical stretch by a factor of a. If a is less than 0, the graph will be reflected in which axis? Well, let's take a quick look. Let's turn this into -3. So you see that it's reflected from this way to this way. So it's reflected in the x-axis. Okay. So the mapping, your y values are, your values are x, which doesn't change, and then your y values change by a factor of a. So a times y to map that new stretch. And we'll do them in this order as well, A, B, H, K. Alphabetical, which is nice. Okay. B is a horizontal stretch. So you notice that B is within the log function. So B causes a horizontal stretch by a factor of 1 over B. So you notice that when we made it 1/2, it stretched it from 1 and 0 to 2 and 0. So you take your normal x, and this time you stretch it by x over b, and then your y value will not change with this kind of stretch. If b is less than 0, the graph will be reflected in the y-axis. So let's go take a quick look at what that would look like. So let's change b to be less than 0 by making it -1/2. So there you go, and you see that it's been reflected over here from this way to this way, so reflected in the y-axis. H, as usual, same thing as everything else, horizontal translation of H units. K, as usual, a vertical translation of K units. So we go from our x value to x. So if H is a positive number, we move to the right. So we go x plus h, and then y, and this one, the x doesn't change, but the y value is shifted by a factor of k. Accident. Okay. Translations of a logarithmic function. So let's see what we can do with this stuff. Use transformations to sketch the graph. So, identify the characteristics of the function. So let's figure this out. Sketch this graph, translate the graph to the left 9 units and up 2 units. So we just start with this graph, log base 3x. So we only have a translation. B is 1, A is 1. So we only have translation, which is left 9 units and up 2 units. Choose some key points to sketch on the base function and examine how the coordinates of some of these key points and the position of the asymptote will change. Each point xy on the graph is translated to become x minus y and y plus 2. So we're only applying a horizontal shift, 9 left, and a vertical shift, 2 up, to every single point that we choose from the original graph. So in mapping notation, it looks like that. Fairly straightforward. Okay, so here's some points that I've chosen. You can verify that these work in here. So 3 to the 0 equals 1. 3 to the 1 equals 3. 3 to the 2 equals 9. Okay? And then we've translated all those. So we just take x minus 9 to get minus 8 and y plus 2. Okay? So 1 plus 2 is 3. 3 minus 9 is minus 6. There are your new points for your new graph, and here you go. If we plotted these 3 points on the original function, okay, which are the same ones as here, these are the translated points. And that's what the function of the graph of the new function looks like. Alright, now taking a look at the asymptote. The asymptote is the y-axis, so in the original function, oh, where's my graph? In the original function, it will never cross the y-axis right here. So your range, or sorry, your domain is still going to be greater than 0 this way. But since we've had a horizontal shift, 9 units left, instead of 0, we shift our asymptote 9 units left as well, and our new asymptote is at x equals minus 9. So it changes your domain as well, because now x will be any value greater than minus 9. Alright, so the vertical asymptote x equals minus 9. The domain, x is greater than minus 9, otherwise an element of the reals. And the range is still everything. It goes down to negative infinity and up to positive infinity. And to determine the y-intercept, put 0 in for x, then solve. So this is what it looks like. This was our function, y equals log base 3, where x is 0, 0 plus 9 plus 2. Okay, so log base 3, 9 plus 2. Log base 3, 9 would mean 3 to the something equals 9. Okay, what is this value? It's 2. So log base 3, 9 is 2. So then we just go 2 plus 2, y equals 4. The y-intercept is 4. So we have the point 0 and 4 for crossing our y-axis. And let's see if that's true. 0 and 4. And there it is right there. Perfect. And finally, to determine the x-intercept, we set y equal to 0. And sorry. It's a little more complicated of a calculation. So when y equals 0, we have this right here. So subtract 2 to the other side. Now, to get rid of log base 3, we have to take the inverse. 3 to the log base 3 of x plus 9. So we take 3 to this power of this side, whatever your base is, that's what your base is here, 3 to that power. And then we take 3 to the power of the other side as well. Okay, now 3 to the power of log base 3x plus 9 will leave us with x plus 9. And you can see here 3 to the negative half is the same as 1 over 3 squared, which is 1/9. And this is how we figured this out. 1/9 minus 9 will be 1/9 minus 81 over 9, which will give us negative 80 over 9. And that's our x-intercept. You might have questions about this one tomorrow, and that's fine. Here's a your turn. Take your time to work your way through this. When you come back, the answers will be here, so hit pause now. Okay, welcome back. Here's the answers to the your turn. So there's what the graph looks like. So you can pause it here to take a look and see if you did everything correctly. Okay, example 2. So we're going to look at reflections, stretches, and translations all in one now. So now you see that here we have an A value of -1 and we have a B value of 2. Now, we don't want X to be paired up with anything because we don't know, it's not very clear what our H value is. So we have to take out a factor of 2, but it still has to stay in the brackets, in the bigger brackets, because we're taking the log base 2 of that 2 still. So we would rewrite it as log base 2, and then in brackets we would write it like this. So divide both things in the brackets by 2, and now it's more obvious what our H value is. H is -3. So B equals 2, H equals -3, and of course K on the end here, K is 0, so that's not going to have a vertical translation. So let's figure out some things here. The equation of the asymptote. This is only affected by the horizontal shift. The horizontal shift is left 3, so the equation of the asymptote, said factor that already, did that already. So if you wanted to sketch it, horizontally stretch it by a factor of 1/2. Since B is 2, the stretch factor is 1 over B, so that's stretching it by a half. And in mapping notation, this is what it looks like. So whatever your x value was in your original function, you now multiply it by a half in your new function. So this is the original function. This one, we mapped all these points, all 4 of these points, and this is what it will look like in the new function when we apply that. And that's not going to want to show up for me apparently, which is weird because it worked perfectly earlier today. Oh well, I'm sure the next one will work. So notice the y values aren't changed from one to the next, only the x values, and all we've done is take each x value and halve it. Okay, so 1 becomes a half, 2 becomes 1, 4 becomes 2, 8 becomes 4. Okay, so we've applied the B stretch first. Now let's apply the A stretch, which all it is in this case, since it's a -1, it's just a reflection and not a stretch. So in mapping notation, we only affect the y value, and those y values are changed by a factor of -1. So we started with the one after we had stretched all of the x values already, and notice those x values are not changed because of the a value. We only changed the y value by a factor of -1. So 0 stays as 0, 1 becomes -1, 2 becomes -2, and so on like that. So this is the one that we had graphed on the last page, and this is the new one, the reflection in the x-axis. So we've taken all the x values stay the same, so x is 1 here and x is 1 here, but now we've turned a -1 into, a 1 into a -1, and a 2 into a -2. So it's simply just flipping those y values. Finally, let's translate horizontally. So 3 to the left. So let's look at our twice stretched function, or our stretched and reflected function. Now we're going to translate each one of these 4 points 3 units to the left. So this half becomes negative 2.5. This 1 becomes negative 2. So they should be here, here. This 2 becomes minus 1. So there. Then you'll see that it's pretty simple moving these each 3 units to the left. In mapping notation, take whatever x value you had, subtract 3 from it. So we had all these x values that we had stretched earlier with the 1/2 factor. Now just shift them all left 3 times by subtracting 3. Okay? So there are your values. You can pause it and take a look at it if you want a longer look. Finally, the vertical translation, which there is none. So we don't have to worry about moving it. Here's your vertical asymptote. It moves 3 units left from 0 to minus 3. So now our range, our domain, will never cross that negative 3 line, so it's always greater than minus 3. Range is still an element of the reals. Now our 2 intercepts, the y-intercept, again plugging 0 in for x. So negative log base 2, 2 times 0 plus 6. So log base 2 of 0 plus 6 is just log base 2 of 6. So negative 2 to the what equals 6. So you could just actually plug this into your calculator if it allows you to do it, rather than doing it this way and then having to do the guess and check model. Finally, the x-intercept is when y equals 0. So set y equal to 0 over here. Try to solve this thing. So dividing off the negative doesn't change it. Now again, log base 2 to this. You can get rid of that log by taking 2 to the power of log base 2 to the 2x plus 6, and then on the other side 2 to the power of 0, so 1 equals 2x plus 6. This is a simpler way to do it. Let's not worry about this. That's nonsense. Okay, so right here. And then solve for x. And you all know how to do that, so there you go. Leave the rest of it to you there. Example 2, here's your turn. So you can hit pause, the answer will be there when you come back. So here's your answers for all of those properties. And you can hit pause if you want to study these a little more. Check, see if you got them right. Example 3, determine the equation given the graph. Okay, so this is working backwards from what we were just doing. So let's take a look at these things. The red graph can be generated by stretching the blue graph of y equals log base 4x. So we need to figure out what the red graph is based on a stretch of this graph. So we know it's still going to be base 4. We never change our base. We just apply the shifts and stretches of A, B, H, and K. So let's see what we've done here. Now notice your vertical asymptote has not changed from 0 to 0, or it's not changed at all, and it's still 0, which means there is no horizontal shift. H is 0, so we have already eliminated that as a possibility. All right? So let's move forward. Red graph hasn't been horizontally stretched, that's what I just said. Okay, now, comparing the graphs. So we look at maybe one key point on the blue graph, the original graph, log base 4x. The key point is 4 and 1, so that's this right here. So let's apply some kind of stretch and shift to make this happen. But we know there hasn't been a horizontal shift because there's no asymptote movement. Okay, so this is not represented by a horizontal shift, it's represented by a series of stretches. So 4, 1 becomes 1 and 1. So what have we done? Well, we have taken that x value of 4 and we have multiplied it by 1/4 to turn it into a 1. So it's been stretched by a factor of 1/4. Now b is always 1 over the stretch factor. So 1 over b equals 1 over 4, and therefore b equals 4. The red graph can be described by this equation: y equals log base 4, 4x. And that's all we needed to do, because notice that there was no stretch of the y value here whatsoever to achieve this point. So this is all we would need to do in order to get that one. That one was pretty straightforward. So here's another your turn. Hit pause. Welcome back. There's your answer. So the red graph is described by that one. Finally, example 4 here. An application involving a logarithmic function. Welding. We know what welding is. So the tint, the filter shade number for their visors is n. And it's defined by this function where t is the fraction of visible light that passes through the filter. Okay? So, shade numbers range from 2 to 14. 14 allows the least amount of light through. So we're given the log function here, and we are asked to figure out what fraction of visible light passed through when we use a tint number, a filter shade number of 12. So let's see what's going on here. So our number is 12, which means we replace n with 12, filter shade number. Now, this negative here, since it's in front of the log and not within this, we can just bump it out and put it with that. Here it is. Now this looks like log t. Since it's not stated explicitly here, this base is 10. So multiply by 3, divide by 7, and negative on the other side as well. So this turns into log t, I'm just going to move it to this side, equals negative 12 times 3 is 36. So negative 36 over 7. So base 10, base, exponent, answer. 10 to the negative 36 over 7 equals t. Okay? So 10 to the negative 36 over 7 equals t. So let's find a calculator here. Google's usually handy. You can go 10 to the power and then put it in brackets of negative 36 divided by 7. And trusty old Google will spit out a number for us. 0.0000072. So 572. Lag issues here. exact same steps. The light.